2.90 to 2.70 Ga. Formation of juvenile Archean crust in the Superior Province, including volcanic plutonic terrains, e.g., Wabigoon and Wawa subprovinces, and metasedimentary belt south of the Great Lakes Tectonic Zone, GLT. This involved widespread mafic to felsic volcanism and plutonism, laying the foundation for the southern Superior Craton in northern Minnesota, Wisconsin, and Michigan. Rock types include greenstone belts, tonalites, and gneisses. 2.86 to 2.84 Ga. Onset of continental arc magmatism in the Wyoming Craton's Bighorn Mountains, northern Wyoming, with emplacement of batholiths ranging from gabbro and diorite to granite. These rocks show magnesian, calc-alkalic compositions, and Nd isotopic signatures indicating mixing of depleted mantle-derived juvenile material with recycled crust, signaling early subduction processes. 2.83 to 2.79 Ga. Continued arc magmatism in the adjacent Beartooth Mountains, southern Montana/northern Wyoming, producing similar batholiths and contributing to the growth of the Beartooth Bighorn Magmatic Zone, BBMZ. 2.8, 2.7 billion years ago, early Neoarchean growth. Wyoming Craton expansion. The Wyoming province, first stabilized in the Mesoarchean, continued to grow as volcanic arcs and sedimentary basins were accreted to its margins. Greenstone belt activity persisted. Volcanic rocks, banded iron formations, BFs, and sedimentary successions were deposited in shallow seas. Craton thickening. Granitoid intrusions, granite, tonalite, granodiorite, added volume and stability to the crust. Metamorphism welded older rocks, transforming greenstones and sediments into high-grade gneisses and schists. 2.8, 2.7 billion years ago, Ga. Early Neoarchean, building the Cratons. Event: volcanic island arcs and greenstone belts. Process: the predominant tectonic process was the collision and accretion of volcanic island arcs, similar to modern-day Japan and oceanic plateaus. Between these arcs, extensive greenstone belts formed. These are sequences of metamorphosed volcanic rocks, basalt, komatiite, and sediments, greywacke, chert, that were later deformed and uplifted during collisions. Location: Superior Craton, Min, Wi. Mi. This was a period of immense volcanic activity. The Wawa-Abitibi terrain, extending into Michigan and Minnesota, and the Quetico subprovince were active island arcs and sedimentary basins. The famous iron ranges of Minnesota and Michigan, e.g., Mesabi Range, Vermilion Range, began forming as banded iron formations, BFs, on the seafloor during pauses in volcanic activity. Location: Wyoming Craton, WYMT. Similarly, the Wyoming Craton was growing through accretion. The Beartooth Mountains of Montana and Wyoming contain extensive Neoarchean crust, including the Stillwater Complex, a massive layered igneous intrusion that is a world-class source of platinum and chromium. Ca. 2.78 Ga. Initial disaggregation of the Proto-Superior Craton lithosphere due to radial mantle outflow, creating a concentric fabric of greenstone belts and shear zones across northern Minnesota and Wisconsin. This, overturn, event stretched the crust, facilitating later reassembly. 2.75 to 2.695 Ga. Major volcanomagmatic event in the southeastern Superior Craton, extending into northern Wisconsin and Michigan, with pulses of calc-alkalic to Shoshonitic volcanism and plutonism. 3 volcanic periods are recorded, including mafic intermediate lavas and associated tonalites, linked to arc subduction. 2.72 Ga. Northern Superior orogeny, southward docking of the Northern Superior Superterrane onto the North Caribou Terrane in northern Minnesota, marking the early assembly of the Superior Craton. This involved arc-related magmatism, e.g., Shoshonitic volcanics at 2.71 Ga, and south over north shearing along NW trending right lateral shear zones. Rock types: granitic gneisses, mafic intermediate volcanics, and minor greywacks. 2.72 to 2.70 Ga. Archean orogeny northward docking of the Winnipeg River terrain onto the North Caribou terrain, suturing to form the English River Belt by less than 2.705 Ga. Deformation included ductile brittle faults and southward overthrusting, with post-tectonic Pluton emplacement cooling by 2.70 Ga. Key rocks, foliated tonalites, granites, wax, amphibolites, and low-pressure granulites in Minnesota's southwestern margin. Ca 2.70 Ga, central superior orogeny accretion of the western Wabigoon terrain to the southwestern Winnipeg River terrain margin, with tonalitic and pyroclastic rock formation, 2.715 to 2.70 Ga. Deformation involved overthrusting, preserved in gneisses and mafic volcanics across northern Minnesota and Wisconsin. 2.7, 2.65 Ga, Mid-Neoarchean, major amalgamation and granite formation. Event, continental collisions and granite intrusions. Process, the numerous island arcs and microcontinents began to collide with each other with incredible force. These collisions caused widespread deformation, folding, and metamorphism of the existing rock. Deep crustal melting generated enormous volumes of granite magma, which intruded upwards, stitching the various pieces together and solidifying the crust. Result: this process, known as cratonization, created the stable, thick, and buoyant continental cores that have survived virtually unchanged for billions of years. Location: Superior Craton. This was the final assembly phase of the Superior Craton, the largest Archean craton on Earth. The various subprovinces, Wawa, Abitibi, Quetico, etc., were sutured together along major shear zones. Vast areas of Minnesota, Wisconsin, and Michigan were underlain by these new granite gneiss complexes. Location: Wyoming Craton. The same process was finalizing the Wyoming Craton. The Beartooth Bighorn magmatic zone was active, pumping huge amounts of granite into the crust, creating the rocks that now form the core of the Teton Range and other mountains. 2.7, 2.6 billion years ago, Peak Craton Assembly. Major orogenic events, mountain building. The Wyoming Craton experienced intense tectonic collisions as multiple microcontinents and volcanic arcs fused, resulted in thickened crust, widespread deformation, and large-scale metamorphism. Black Hills, South Dakota contains rocks dated to 2.6, 2.7 Ga, likely linked to these accretionary events. Bighorn and Wind River Ranges, Wyoming, show strong deformation from this tectonic activity. 2.69 Ga, Shabando-Winian orogeny northward collision of the Wawa-Abitibi terrain with the growing Craton, suturing beneath the Quetico Belt in northern Minnesota and Michigan. This ended arc magmatism in the Winnipeg River superterrane, 2.695 Ga, and produced Sanukitoid plutons, 2.695 to 2.685 Ga, from slab breakoff. Events included intra-arc transpressive deformation and foreland basin development in graywax and layered volcanic plutonic rocks. Ca 2.68 Ga, high-pressure collisional tectonics in the northern Teton Range, northwestern Wyoming, where gneiss units were juxtaposed along myelinitic shear zones. Peak granulite facies metamorphism, greater than 10 kbar, greater than 700 degrees Celsius, followed by decompression melting produced leucogranites, indicating Himalayan-style continent-continent collision. 2.68 Ga, Minnesotan orogeny northward collision of the Minnesota River Valley terrain, southwestern Minnesota, with the composite Superior Craton along the Great Lakes tectonic zone. This involved northward subduction of an oceanic slab, with the terrain thrust beneath the Craton. Associated paraluminous granitoid magmatism and Neoarchean metamorphism overprinted older gneisses, recording terminal suturing. 2.65 to 2.63 Ga, accretion of oceanic affinity meta-igneous and immature metasedimentary terrains along the southern margin of the BBMZ in the southern Wind River, Granite, Sierra Madre, and Medicine Bow Mountains, central southern Wyoming. This preceded emplacement of the Lewis Lake batholith and involved widespread deformation. 2.65, 2.5 Ga, Late Neoarchean, Supercontinents and Atmospheric Revolution. Event: Formation of Kennerland. Process: the newly stabilized Superior and Wyoming cratons, along with other cratons like the Slave, Canada, began to assemble into one of Earth's first hypothetical supercontinents, Kennerland. Location: the assembly likely involved the collision of the Superior and Wyoming cratons, though the exact configuration is still debated by geologists. This supercontinent was situated near the equator. Event: the Great Oxidation Event, GOE. Process: throughout the Archean, cyanobacteria in the oceans had been performing photosynthesis, producing oxygen as a waste product. For hundreds of millions of years, this oxygen was immediately absorbed by dissolved iron and other minerals in the oceans, forming banded iron formations, BFs. The crisis: by the late Neoarchean, these oxygen sinks became saturated. Oxygen began to accumulate catastrophically in the atmosphere and surface oceans, poisoning anaerobic life and causing a global mass extinction of microbial life forms. This is the Great Oxidation Event. Evidence in the U.S. The vast banded iron formations of the Mesabi Range, MN, and the Gogebic Range, MI/WI, are direct evidence of this process. They represent the world's most important iron ore resources precisely because of the chemical changes wrought by the GOE. Event: onset of glaciation. Process: the rise of oxygen, a greenhouse gas, and the drawdown of atmospheric methane, which reacts with oxygen, likely triggered the planet's first major ice ages, which continued into the subsequent Paleoproterozoic era. Ca 2.64 Ga. Emplacement of strongly paraluminous leucogranites, a saturation index greater than 1.1, across the Wyoming craton, e.g., Beartooth Mountains, derived from partial melting of aluminous metasediments. Linked to collision between Wyoming and Superior cratons, contributing to Superior supercraton assembly. 2.60 Ga. Continued production of paraluminous leucogranites from metasedimentary melting, signaling waning collisional orogeny in the Wyoming craton, e.g., Laramie Mountains. 2.6, 2.55 billion years ago, stabilization of continental nuclei. Continental lithosphere becomes rigid. The Wyoming craton reached a stable configuration, forming one of the strongest cratonic blocks in Earth's history. Some crustal blocks may have been emergent land, true continental land masses above sea level, marking a shift toward larger continents. Sedimentary evidence. Weathering products, sandstones, shales, appear, suggesting more continental crust above water and active erosion. Continued deposition of BFs reflects interaction between volcanic activity, seawater, and oxygen-poor atmosphere. Ca 2.56 Ga. Intrusion of Neoarchean granitoids in the Black Hills, western South Dakota, part of the Wyoming craton's southern extension. These include tonalitic to granodioritic plutons with inherited 2.90 Ga zircon xenocrysts, indicating recycling of older crust during late-stage magmatism. 2.55, 2.5 billion years ago, late Neoarchean global connections. Kennerland supercontinent hypothesis. Around 2.55 to 2.50 Ga, the Wyoming craton, U.S., likely joined with the Superior Province, Canada, Kopval Craton, South Africa, and Pilbara Craton, Australia, to form one of Earth's first true supercontinents, Kennerland. Black Hills and Minnesota River Valley terrains. Possible correlations to other Archean cratons, suggesting transcontinental tectonic links. Oxygenation precursors. The deposition of late Neoarchean banded iron formations marks the beginning of changes in ocean chemistry that led to the Great Oxidation Event in the Paleoproterozoic, 2.4 Ga. 2.51 Ga. Emplacement of the Laramie batholith granite in the northern Laramie Mountains, southeastern Wyoming, with RB Senior whole rock ages marking final Neoarchean plutonism in greenstone granite associations. Ca 2.50 Ga. Intrusion of granitic gneiss, e.g., Rawhide Buttes granite, into late Archean Wayland Group metasediments and metavolcanics in the Hartville Uplift, northeastern Wyoming/South Dakota border, stabilizing the Wyoming Craton's margins.